Hello everyone, let's go ahead and take a look at the second method for finding volumes of revolution, which is called the shell method. Now before we go ahead and do that though, I would like us to go ahead and review the disk washer method. So let's go ahead and take a look at that first. Let's assume that we have two functions, one being y is equal to f of x and the other being y is equal to g of x. It is going to be rotated about the x-axis, and we're talking about the area that's in between these two functions on the closed interval from a to b. So remember that we said that if we wanted to go ahead and find this particular volume of revolution, then we use the initial statement v is equal to pi times by the interval from a to b of the larger radius function squared minus the smaller radius function squared d of x. So what we said then was that the key to being able to find this is that you have to identify what r of x is, or the larger radius function of x. And in this particular case, of course, it's going to be f of x. And you also need to be able to identify the smaller radius function, and in this case, it's going to be g of x. Now, the one thing that we always go ahead and need to make sure and identify and keep in mind is that the rectangle that we draw is always going to be perpendicular to the axis of rotation if we're using the disk and washer method. Okay, so three keys. Larger radius function, smaller radius function, the rectangle is perpendicular to the axis of rotation. Now, the reason why we need to go ahead and pay particular attention, especially to this, is because when we deal with the shell method, which is our new method, the rectangle is parallel to the axis of rotation, which is going to be very different. Now, when we go ahead and talk about the shell method, what exactly is a shell? Well, what they're referring to is a cylindrical shell. So let's go ahead and take a look at this diagram here. And notice that if we wanted to go ahead and calculate the lateral surface area of a cylinder, what we need to be able to do is we need to be able to calculate the circumference of the circular base of the cylinder and multiply it by its height. If we get that, we find the lateral surface area of the cylinder. So in other words, we need 2 pi r times it by h. So the key for us then is to be able to identify what r is and what h is. Because if you know what r is, or the distance away from the axis of rotation to your cylinder, and you know the height of your cylinder, then you can very easily go ahead and determine the lateral surface area of that particular cylinder. So take a look at our diagram. Now notice I'm using the same y is equal to f of x, y is equal to g of x from a to b, but notice what happens is that our rectangle is parallel to the axis of rotation. So when the disk and washer method, we actually had the axis of rotation being the x-axis. But for our case right now, if we're going to use this rectangle, call it d of x, we need to know that the axis of rotation is now going to be the y-axis. And these are all the shells that you're actually going to be creating. And then when you go ahead and add all of those lateral surface areas, you're going to come up with volume. So this is what we have then for our initial statement. We have v is equal to 2 pi, so notice the connection there, from a to b, p of x, h of x, d of x. Okay, so I'm thinking that you can go ahead and identify what those are. The r, or the radius, which is the distance again from the axis of rotation to your rectangle, is going to be designated as p of x. And h, or the height of the rectangle, is just going to be h of x. Okay, and then it's going to be, of course, so important to recognize that the rectangle is parallel to the axis of rotation. Okay, so let's go ahead and take a look at a couple of examples. Now, in this particular example here, a very straightforward one, it says y is equal to x squared on the closed interval from 0 to 2. And let's go ahead and revolve this about the y-axis. Now, what we're going to do then, of course, is we're going to use the shell method if we go ahead and designate our rectangle to be parallel to the axis of rotation. And we're going to go ahead and talk about that as d of x. So here's our initial statement again, 2 pi from 0 to 2. Of course, because we're looking at the x values, because our variable of integration is x. So p of x, h of x, d of x, we need to go ahead and identify what r is R, again, remember, is the distance away from the axis of rotation to the rectangle. Now, that's just going to be the value of x because it's going to be able to vary anywhere from 0 to 2. And then the height, or h of x, of our particular shell is going to just be generated by the function itself, which is x squared. So if I go ahead and substitute then into my formula for the volume of revolution using the shell method, I get 2 pi times the integral from 0 to 2, x times by x squared d of x, and if you go ahead and do that calculation, you'll come up with 8 pi. Now the thing is that we also want to go ahead and take a look at what happens if we were to go ahead and use the disk or washer method. Would you be able to come up with exactly the same result? And of course the answer is yes. But let's go ahead and take a look at how it differs in terms of your approach. So if we were to go ahead and use the disk or washer method for exactly the same situation, we need to go ahead and make sure that our axis of revolution is going to be the y-axis, and therefore our rectangles have to be perpendicular to the axis of rotation. Therefore we're dealing with this rectangle here, and therefore our integral of our variable of integration is going to be y. So if we go ahead then and take a look at what our initial statement was, it's going to be pi times it by the integral from 0 to 4, because those are the y values that are generated, times it by the larger radius function in terms of y squared, minus the smaller radius function in terms of y squared, d of y. So again, it's going to be very important for us to be able to identify what r of y is, the capital R of y is, and the lowercase r of y. Now, r of y, of course, is just going to be 2, because if we go from here all the way to this endpoint there, then that's going to be 2, because that's going to be our larger radius. And then if we go ahead and take a look at what our smaller radius, this is in terms of y. Our smaller radius and our larger radius in terms of y. Okay, then we know that r of y is just going to be equal to the square root of y, because it's just going to be determined from this point here to this curve there. So what I come out with then is that the volume is going to be pi times the integral from 0 to 4 of 4 minus y, d of y. And again, if you wanted to go ahead and solve or evaluate that simple integral, you would come up with exactly the same value of 8 pi. So notice that the shell method and the disk and washer method, they're going to be able to give you exactly the same result, so long as you're dealing with the same volume of revolution. It's just that the mathematics may be a little bit more tricky because you need to go ahead and adjust. Say, for example, in this case with the disk and washer method, we needed to go ahead and adjust and solve for y and x in terms of y. Okay, so let's go ahead and take a look at another example here. Now, this example says if you have y is equal to x cubed plus x plus 1 on the closed interval from 0 to 1, and let's go ahead and rotate this about the line x is equal to 2. So I've gone ahead and I've drawn the diagram here of what this function is on that particular interval, and of course here is going to be our axis of rotation. Now, since our axis of rotation is this, and I wanted to go ahead and use d of x, then what I'm going to do is, of course, make this parallel to that axis of rotation, and therefore I have to use the shell method. So b is going to be equal to 2 pi times the integral from 0 to 1, of course, because I'm going from 0 to 1, because our variable of integration is x. And therefore I need to go ahead and determine what r and h are in terms of p of x and h of x. Now, p of x, of course, is just going to be 2 minus x. Now, let's go ahead and just very clearly identify why that's true. It's 2 minus x because as this rectangle varies anywhere between 0 and 1, the distance from your axis of rotation to that rectangle is always going to be 2 minus x. So let's say, for example, if that's an x value right there, then that's 2 minus the x value, and that's going to be your radius. Now the height, of course, is just going to be very simply the function itself, which is x cubed plus x plus 1. And so if you wanted to go ahead and take a look at what that integral would look like, it would look exactly like that. Now again, you can go ahead and do that calculation if you wish. The purpose of actually taking a look at this example is to show you why the disk and washer method is not possible. Right? The shell method is, disk washer is not. Disk washer method is not. Now, same situation here. There's a lot of different notation here, but same situation that we have up there. Axis of rotation, x is equal to 2. Remember now, being that we're trying to do this using the disk or washer method, our rectangles have to be perpendicular to the axis of rotation, and therefore we're dealing with rectangles here, which is d of y, so our variable of integration is y. So now the thing is that I need to actually split this up. I need to split this up into two different parts. I'm going to take the volume from y is equal to 0 to y is equal to 1, from here to here. And then I'm going to have to deal with the volume from y is equal to 1 to y is equal to 3 there. And I'm hoping that everybody sees the reason why. It's because when I go ahead and I take a look, say for example, from the volume from y is equal to 0 to y is equal to 1, the larger radius in terms of y is just going to be this length. It's going to be all the way from 2 all the way to 0, which means that that is always going to have a constant value of 2. In the same respect, the smaller radius in terms of y is always going to be equal to 1. So therefore, I got this 2 squared minus 1 squared, and I can easily go about finding that integral. Now the problem comes when we actually go ahead and take a look at the volume from y is equal to 1 to y is equal to 3. So I go ahead and say pi from times it by the integral from 1 to 3 of the larger radius in terms of y, quantity squared, minus the smaller radius in terms of y, quantity squared, d of y. Now, the larger radius in terms of y is going to be 2, because it's going to go all the way from here to here, and I'm going to subtract that much. So that means that I have to actually go ahead and find out what that function is in terms of y. Now when I go ahead and I take a look at the smaller radius in terms of y, that's always just going to be a constant 1. So that's not the issue. The issue here is this. I got to get this in terms of y. And we knew that y was going to be equal to x cubed plus x plus 1. I'm hoping that everybody sees the issue here. When we actually did this example here, and we wanted to solve for x in terms of y, then we just took the square root of both sides, so we get x equal to the square root of y. In this particular case here, I can't solve for x in terms of y. And because of that, I'm not going to be able to actually use the disk or washer method in order to go ahead and solve for the volume of revolution. So, it's going to be important then that we actually have both the shell method as well as the disk or washer method, because when we go ahead and take a look at our axis of rotation, it's going to be important for us to recognize, do I want my rectangle, in other words these blue rectangles, do I want that blue rectangle to be parallel to the axis of rotation, or do I want it to be perpendicular to the axis of rotation? Now the key to that, if we go ahead and take a look at this example here, is that if I was to go ahead and take a look at this d of y, the endpoints of that rectangle, it's constant up to here, and then all of a sudden it switches to a different function. When you have that situation, that's usually the more complex way of approaching the volume of revolution. As opposed to this situation over here, where the two endpoints of that rectangle are always going to be consistently on the same curves. So that's going to help you determine, do I want it to be parallel or perpendicular to the axis of that rectangle, to be perpendicular or parallel to the axis of rotation, and once you go ahead and determine that, you know which method you need to use, either the shell method or the disk washer method. Okay, so we'll go ahead and take a look at more examples the next time that we meet in class. See you then. Bye-bye.